Continuing our lecture regarding the thyristor, the classical thyristor, the SCR1, we studied and described the IV characteristics. It's now the case to study the behavior of the device, turn on and turn off dynamics. We yet know that these devices are quite slow for very high power, but switching frequencies that are few hundred hertz, no more than that. The device is one SCR, one thyristor, high power thyristor. They are also available in small discrete as a discrete devices in small packages. But most of the times, for very high power, they are very big devices. Usually for devices that carry several kiloamps, one single device occupies an entire wafer. In this scheme here, you see the top view of one single wafer. This is the diameter. This is a 2-inch diameter wafer. This is more or less 5 centimeters of diameter. And we will have the here we have a mistake. This is not the anode. This is the cathode, and this is the gate. The cathode contact is very large. The gate contact is smaller. You expect smaller current to be carried from this side. The bottom, on the bottom, we have the anode terminal. As you can see, this length here is very large, around 2 centimeters. While the thickness of the device, even if this device is quite thick, maybe also 1000 micrometers of thickness, this is much larger than the length of the contacts is much larger than the thickness. This means that two-dimensional or three-dimensional effects are very important for these devices. This is the symbol that we have seen more than once. Two-dimensional effects during turn-on. This is the section of the device during turn-on. We know that a current pulse is needed to trigger the device from the off state to the on state. There is a gate current entering from here. This gate current is the base current for this NPN transistor. This base current activates the NPN transistor that provides the base current for the PNP transistor. The PNP transistor is activated also, and we have the injection of a large amount of carriers here. What actually happens that at the beginning, when the gate current is just above the triggering, then we are above the turnover voltage, there is a high injection region that is only below the gate. In our previous layout here, just in the middle of the device. It's like we are activating just this small thyristor here, not the entire very big, large area thyristor. When the first region is activated, there is a lateral spreading of the carriers that move in this direction and in this direction. And while they move, further areas of the device are activated. And finally, the entire device will be on. This spreading of the carriers is just carrier diffusion. The electric field in the lateral direction is very small. The voltage is between anode and cathode. This means that there is no large electric field in the lateral direction. Only when the entire wafer is full with the carriers, we are in the actual real on state. This is a problem for the turn-on transient. The limitation is on the derivative of the anode current during turn-on. We don't want to increase the current so fast that when the current is at its maximum, the entire device is not yet activated. If this happens, this value is usually indicated in the datasheet. The entire current, the load current, will flow just in a small portion of the device, in the central part of the chip. And this means that the current density will be much larger than the expected value. Assuming that the entire device carries the current, I have a certain density of current density. If the actual area is 1/10 or 1/100th, this current density is much larger, is 10 times or 100 times larger. And this means that there will be a very strong power dissipation in a small area with an acceptable temperature rise and device failure. Please remember, these are bipolar devices. Bipolar devices are very weak when it comes to temperature. If there is an uneven distribution of the temperature, we know they have also a positive temperature coefficient with of the current. This means that if the central part of the device becomes very hot, it will carry more current, and it is possible that you are not able to switch on the entire device, and all the current flows in a small area. The speed of the lateral carrier propagation is few hundreds of micron per microsecond. This means that the current rise time must be in the range of few hundred of microns if the cathode dimension is a few centimeters. This is just a physical limitation. This means that the switching time cannot be faster than 120 microseconds. And this means the very slow switching time for the devices. If we recall the diode, for example, we have seen fast recovery diode, the switching time was below microseconds, it was 30, 50, 100 nanoseconds. Here we are talking about 100, 200 microseconds just to switch on the device. Then you must keep the device on for a certain period of time in order to provide the energy to the load, and then you have the turn off. The entire period means is 1 millisecond, few milliseconds. And here we arrive to 100, 200 hertz for switching time, switching frequency. Solutions. In order to improve the limit on the current derivative, we need to increase the gate current injected into the device in order to force a larger turn-on conduction area. This is, for example, done here, where the gate area is not only the center of the device, but also these regions, this radius here. Obviously, if you have a larger gate area, the gate current will be larger. This is a junction. This is the base and this is the cathode. This is a junction. If you want to switch on this junction and this junction is very small, you need small current. If the junction is very wide, there is a lot of gate area, the current will be larger. And this means larger latching and holding current, and some problems, higher problems for the driving circuitry that needs to carry larger current. This is also, you can also increase the current if you can, but also this is a problem on the device. Even if this can slightly shorten turn on and turn off time. The topic is quite important. Many solutions have been provided, but for example, there is also this possible solution. You have in this circuital model of the thyristor, you have a pilot small area thyristor here that you activate with a gate pulse. This is similar to a Darlington configuration for the BJTs. This pilot thyristor is actually providing the real gate current for the main thyristor. Since this thyristor provides a lot of current, this means that you can amplify the gate current in a certain way. This is the circuital model, but in reality you don't have a pilot thyristor separated by the main thyristor. You can have both of them integrated on the same chip. And this reduces the issue on the gate. Obviously, this probably will have problems on the switching, because when you switch, it only have to switch first this device, then this device. There will be an increase of the delay. Turn-off dynamics. We have a limitation on the voltage derivative during turn-off. We have seen that we have a limitation during turn-on. When you turn on the device, you have a current increase, and you need to limit the current derivative. When you switch off the device, you have a voltage increase. The voltage goes up to the bus voltage, and in this case, we have a limitation on the maximum voltage derivative. This also will determine the maximum speed of the device. The problem is that if you have a too fast increase of the anode to cathode voltage, it can happen that after the turn off, you are turning off the device can automatically switch on again. So you try to switch off the device, and the device remains on after a short period. And this is very, very dangerous. This can be explained recalling the two bipolar junction transistor model that we introduced in slide 17, and that is reported below. In this model, we also highlight the collector to base parasitic capacitance that is present into the device. We can see that if the anode to cathode voltage has a rapid increase, this voltage will increase quite fast. Since a voltage increase on the capacitance, this is a non-linear capacitance, however, let's imagine that this is a capacitance, normal, conventional capacitor. When this voltage increases, it means that there is a current that goes in this direction, the blue solid line. And this current goes into the base of the Q2 transistor, BJT. And this means that this is a triggering pulse, current pulse for the thyristor. This means that if this anode to cathode voltage increases too fast, we are actually switching on the device without applying a pulse of current. And this is obviously a significant problem. Also, for the limitation on the voltage derivative, there are possible solutions. You can, as an example, use cathode shorts. These are shown in the figure. The actual structure of the device is slightly different. You have the conventional 4-layer structure with the N plus, P base, N base drift region, and P anode. In addition, you have these holes, let's say, in the cathode that are shorts between the cathode and the base. From the electric point of view, these shorts are very difficult to understand. If I look at this figure and watch the voltages, I just see that this gate is shorted to the base that is shorted to the cathode. This means that there is no voltage between cathode and gate, and there is no possibility to switch on the device. And it seems that this N plus region is just there to waste silicon area. Actually, you have to imagine this structure like it really is. A very wide region. The cathode region is 2 centimeters. It's very big. And the cathode shorts are small holes here and there, very wide apart. This means that when I apply a gate pulse, there is still a large current flowing, that a portion of this current will be collected by the cathode, short. The other part will just activate the bipolar junction transistor. This is actually reducing the gain of the base. This is like making a smaller cathode or diverting a portion of the base of the gate current to the short, but only a portion of that. The remaining portion of the current will switch on the device. It will be more difficult to switch on the device. You will probably need more current, and then which is the advantage? The advantage is that when the anode to cathode voltage increases, we know that in this case, since this is positive and this is negative, this junction is forward biased, this junction is forward biased, this is the junction that is reverse biased. This P to N minus base junction is reverse biased. There is a depletion region that grows here, and this means that there are a number of holes that are pushed away from the junction. This is actually the base current, the unwanted base current. But if the shorts are here, a portion of this current will be short-circuited through this P plus contact. These shorts will collect some of the displacement current and will reduce the possibility of the transistor to be turned on due to an increase of the anode voltage. You can actually see these cathode shorts also like a reduction of the gain of the NPN transistor. The equivalent emitter is less effective. There is less injection of electrons. There are also other advantages resulting from the use of cathode shorts. Since we are reducing the gain of the NPN transistor, we are closer, the breakdown, the forward turnover point, the breakover point in forward blocking mode is closer to the ideal voltage. There is lower plasma injection because the injection of plasma is from this P plus region holes injected here and N plus regions injected here. But since there is less area for the cathode, there is less injection. And this means that there is a reduced number of carriers, and this means that the device is faster. I can switch it on and off, switch off faster. But there are, however, disadvantages. First of all, the trigger current will be larger. because when I inject carriers through the base, through the gate here, this current, this whole current, a portion of this current will just be shorted, this will just be shorted through the cathode shorts and will not be effective in triggering on the device. Plus, since I inject a reduced amount of carriers, the conductivity modulation here is reduced, is slightly smaller. And this means that the resistance of this region in the on state is larger. There is always a trade-off. The cathode shorts are useful in improving the turn-on, turn-off dynamics, but they will provide more difficult driving and increased on-state voltage drop. In a similar way, it is also possible to use anode shorts to improve the DVT reading. You can also use some N+ shorts here that will work more or less in a similar way. More or less. There are differences. But you can also have shorts here. Here you just see this short, like from an electrical point of view. In a real device, the problem when you decide to use anode or cathode shorts, the problem is in these large area devices, how many cathode shorts do I use? Which is the area of each cathode short? How far one from the other? Is it better to use more cathode shorts, more small cathode shorts, or a big one? Everything is a layout problem in the end, and it is really difficult to optimize in this case. Now, turn on and turn off waveforms for the classical theorist. The turn on dynamics is sketched in these plots, starting from T star when the IG current pulse is applied. This is the gate current, the pulse. We imagine this gate current, the gate pulse like an ideal rectangular pulse. And this is the anode to cathode and the device current. First of all, after the gate pulse, we have an initial delay time. This is the time needed to reach the triggering condition. If we remember well, for low gate current and low forward voltage, the sum of alpha 1 plus alpha 2, the two gains, is smaller than 1. And the first thing that happens while the gate current increases is that alpha 2 increases up to reaching the triggering current. Up to this point, the current is still 0. Then there is the rise time, that is the time needed to create the high injection region and the conductivity modulation near the gate region. In this case, we are assuming that we have a resistive load because in the same time the voltage is decreasing. After the device is turned on in the vicinity of the gate region, there is the spreading time, the time needed for the carriers to spread all over the device. And this is a quite long tail. Only after the device is completely on, it is safe to remove the gate pulse and bring to 0 the gate current. And the device will stay on. Otherwise, you risk that the device will switch off again. One question that has not been answered yet. We say more than once that the classical thyristor, the Silicon Controlled Rectifier, SCR, cannot be turned off by a negative current pulse on the gate. Also in this case, the problem is not the circuital model. If you watch and study the circuital model with two BJTs, you will see, and as we will see in a few slides, that it is possible to switch off the devices with a negative current pulse. But in this case, we have the problem that the device is actually very big. The gate region is far away from the latest and farthest places of the cutoff. What happens if this cathode region here is very, very wide and the gate region is just in the middle, is that if I apply a pulse of negative current, this will actually remove the plasma in the middle of the device here. This is actually switching off the device in the middle. But there will be also a large base current coming from these very wide, very far away places of the thyristor. And this large base current will cause a voltage drop on this layer. This voltage drop at a certain point of the device will be large enough to switch off the device. And this means that these regions far away from the gate will stay on and will be on even if there is a negative gate current. This is actually also dangerous because you are concentrating the active region just in the portions that are very far from the device. As soon as you remove the gate current, the carriers spread again and the device is still on. But you are not able to switch off the device. The only way to switch off the SCR, as said before, is to reduce the anode current below the holding value. Only in this case, the sum of the two alphas will be smaller than 1, and the regenerative action will be destroyed, and in the end, the device switches off. And this can be done reversing the voltage. If you reverse the voltage, at a certain point the current decreases, becomes negative, goes below the holding value, and the device is off. Turn-off waveforms. The turn-off waveform is then caused by a reversing of the anode to cathode voltage. It's very similar to the one of PIN diode. We have said this at the beginning of the lecture on the classical thyristor. You have the plasma in the thyristor. Before switching off the device, you need to remove the plasma. What you actually see is that the current, anode current, starts to decrease. It will go below the holding value and then will go also negative because the device is still on. It's not able to support voltage and the current will go negative. And here the carriers are extracted from the drift region and P-base region. At a certain point, the carriers will be almost gone. The junction will start being reverse biased. And only at this point, the anode to cathode voltage starts to increase and starts to decrease, becomes negative, and we go in the reverse blocking condition. You can also see that there is an overshoot. This overshoot is usually caused by inductive parasitic inductances. Without parasitic elements, this voltage should go up to this value. This is the bus value, negative bus value, but without the overshoot. This concludes our study of the classical thyristor